Good morning, friends. Welcome to my physics platform, which is meant to promote convergence of physics lovers. Today, we'll be discussing about the concept of work. The name of the entire chapter is Work, Power and Energy. So we will be discussing all these concepts in sequence. Well, today we start with the concept of work. Now, how do we define work in physics? Let us imagine that a body is moving along a curve. So, this is the trajectory of the body, and at any general instant, suppose the body is somewhere here. Its velocity is along the tangent, and the acceleration may be in some other direction. Now, in conformance with this law, F equal to ma, Newton's second law, this is the net force. So from here it is obvious that the direction of the net force is same as the direction of the acceleration. So suppose the acceleration is in this direction. So the net force must also be acting in this direction. And suppose the angle between the velocity vector and this is the force, net force, the force vector is theta. Okay. Also we know that V equal to dr by dt. This is how we define velocity. So the direction of velocity vector is same as dr vector. Dr vector is a differential displacement vector. Okay. So the velocity is in this direction, we know that, because the velocity, this is the instantaneous velocity, and the instantaneous velocity is always along the tangent. So the direction of the instantaneous velocity and the differential displacement vector, that is dr vector, is same. So this is also the direction of dr vector. Now we would like to define what is the work done by this net force on this particle during a differential displacement of the particle in a differential span of time dt. Let us call that work a differential amount of work. Let us call that work dw. dw is defined as f dot dr. dw is a differential amount of work, and F is the resultant force or the net force which is performing this work during a differential span of time dt. So during that differential span of time dt, the displacement of the body is dr vector. Now what is the total work performed by the net force as the body moves from this point to this point? Its total work will be integral of F dot dr. This is the definition of work. So see, the work performed by this force will be zero if either the force is zero or this dr vector is zero, that is the point of application of the force is not moving, or the angle between these two vectors is 90 degrees because this is the dot product. So under these three circumstances, the work done by the force will be zero. But to get a better picture of this idea and to get a better picture of the concept of work, we will dwell into some examples, and those examples will make the concept clearer. So but before embarking upon the examples, let us see what happens if this force is a constant force. Okay, we are imagining that a body is moving along an arbitrary curve and a constant force is acting on the body. Then we would like to explore what happens. Fine. So let us imagine that a body is moving along some arbitrary curve. Suppose it is moving like this. And at an initial instant the body is here, and finally it lands somewhere here. And during this period, during this motion, during the course of the motion, a constant force is acting on the body in this direction, in the horizontal direction. This is a constant force. We know that the work done by the force, the total work done is integral of F dot dr, and we would like to know what is the work done by this constant force. Fine. Okay, now as the body is slipping down, it's moving along a general trajectory and along an arbitrary curve. Suppose at any general instant of time the body is somewhere here. And this is the direction of dr vector. So dr vector is along the tangent. It's a differential vector, tiny vector along the tangent. It represents the displacement of the body during a differential span of time. So, and suppose later on the body is somewhere here, then this is the direction of dr vector. So you see the dr vectors, the tiny dr vectors are always along the tangent. So we keep drawing dr vectors. They are always along the tangent. So these arrows are representing dr vectors. Body is somewhere here, this is dr vector. Body is here, this is dr vector. But the force acting on the body is constant, so this force can be dragged out of the sign of integration. So it becomes like this. So here we are encountering this term which is integral of dr vector. Integral of dr vector means, integration means summing up or adding up. So what we are doing here, this entire operation represents the summation of dr vectors. This entire thing is dr plus dr plus dr, dr vector plus dr vector plus dr vector plus dr vector. So you are adding dr vectors here. So this is vector integration. This vector has been integrated. So this quantity which I would call dr, which is dr vector, this is something like this, integral of dr vector. This is something like this, dr vector plus dr vector plus dr. You keep on adding these terms up to infinity. And this is integral of dr vector. Now this vector addition, this is on the right hand side you see it is vector addition. Vector addition will represent the resultant, and the resultant is the displacement. So if you keep adding these vectors, these tiny dr vectors from this point to this point, then the resultant will be this straight line. This straight line will be the resultant. So this summation will be this straight line, the displacement, let us call it r vector. So this will be equal to r vector. This is vector integration. So this boils down to f dot r vector. Now the angle between f vector and r vector is theta, which is quite obvious from here. And you extend this line and drop a perpendicular from this point to on this line. This is 90. Now you just use the formula for dot product. This boils down to mod of f into mod of r into cos theta. We have dropped this vector notation. So now this is magnitude of the force f, and this is magnitude of the displacement, and this is cos theta. Theta is the angle between f vector and r vector. Now you see this term r cos theta. Now from this triangle, now this is r and this angle is theta. So r from this triangle, this distance is r cos theta. Let us call it d. So this r cos theta can be replaced by d. So you get dfd. So this is the work performed by a constant force as the body moves along some general arbitrary trajectory. And so this is the net force performed by that net work performed by that constant force. So you can remember it like this, that this work is equal to F into D. Now what is D? D is the displacement of the body in the direction of the force. This is not the actual displacement, but d is actually the magnitude of the displacement of the particle in the direction of the force. And d is not the magnitude of the actual displacement. The magnitude of the actual displacement is this length. So, I can give you an example of this, practical example. Another one. Like suppose a body is moving along an incline. This body is slipping down this incline, and during its journey from this point to this point, a constant force mg is acting on the body. We are assuming that mg is constant. So it is constant. Constant, how do you realize that the force is constant? How do you come to know that force is a constant? If it is constant, because it's a vector quantity, if it is constant, then its direction will be same and its magnitude will be same. The direction will be same means that the force vectors will be parallel. So all the force vectors will be parallel. As the body slips down or moves, the force vectors will be parallel, because force is a vector quantity. Parallel means they are having same direction, and the magnitude of the force must also be same, because a vector is identified by its magnitude and direction. So a constant force means the direction is same, that is the force vectors remain parallel to themselves, and the magnitude is same, that is the size of the arrow remains same. Suppose the force is 5 Newton at this point, so it is also 5 Newton at this point. So as the body slips down the incline, coming back to this example, mg is constantly acting. Mg is a constant force because it is constantly acting in the downward direction. But as the body slips down, suppose this height is h, then what is the displacement of the body in the direction of the force? It is equal to, what is the magnitude of the displacement of the particle in the direction of the force? It is equal to h. So the work done by this constant force will be mgh as the body slips down. Now suppose we are conducting experiment in the reverse order. We are making the body move from this point to this point, that is reverse journey. So in this motion or in this movement, you see mg is acting downward, but as body is moving from this point to this point, then the displacement along the vertical direction is this. So mg and this displacement, the magnitude of this displacement is h, but mg and this displacement are in opposite direction. So the work performed by this force in the reverse journey will be minus of mgh. Okay, now this concept, I think this concept must have cleared some speck of doubts which might have been in your mind. Okay, now we will see some other examples, explore some other possibilities, and let us see what is the meaning of work. Through those examples, we would like to understand the meaning of work in greater detail. Let us say that there are two objects, A and B. This A is placed over B, and they are moving with, suppose A is moving with some velocity v1 and B is moving with velocity v2. Fine. And let us say that v1 is greater than v2. Okay, and now we are imagining that some friction is acting at this interface. The surfaces are rough, so there is some friction in this at this interface, friction between the two bodies. Okay, now what is the desire of this friction? The friction always desires that both the bodies move together as a common entity, as a common unit. So what is the desire of friction? That there should not be any relative motion between the two bodies. So suppose this body, so ultimately friction would like that both the bodies move together as a single unit. So it restricts or prevents the relative motion. So suppose this body, as in this example, this body is moving faster than this body. So friction would like to slow it down. So friction will act in this direction on body A, and this, because this body is moving slower, so friction would like to speed it up. So in that pursuit, friction will act in the direction of the velocity on body B. And these two forces are acting in action and reaction pair in conformance with Newton's third law. Now, okay, now there is one a very drastic assumption that we are making. I would like to make here is, and I would like to be very clear and very strict about it, that we are assuming that in this example, we are assuming that the bodies are rigid and the bodies are performing translational motion. So the bodies can be assumed to be point-like. In our example, we are assuming the bodies to be point-like and the bodies to be rigid. So which is a very, I would say, a very ideal example, a very ideal assumption. So which assumption is, I would like to emphasize upon, which is actually not possible, but let us assume it for the time being, just to understand how work how work operates. Okay, now we are assuming that, again I would like to emphasize upon, that the bodies are absolutely rigid, no relative motion between the parts of the body, and the body is, both the bodies are performing translational motion, so bodies are point-like. Okay. Now as the body A is moving in this direction, friction is acting in the opposite direction, so it will perform negative work. So the work done by this friction will be minus of F into a small into a differential displacement, which will be V1 into dt. dt is a differential span of time during which a body travels a differential distance. Okay, now this is the work done on body A by this friction, and what is the work done on friction on body B? If you observe here that the direction of friction and the velocity of the body is same, so friction is performing positive work on body B, so it will be plus F into V2 dt. So this can also be written as, if you take this common, V dt, V into F into V2 minus V1 into dt. Now this is dw. This dw is the work performed by friction on this entire system at this interface in a differential span of time. Now you see that as V1 is more than V2, so this will definitely be negative. Okay, now V1 is also, as V1 is more than V2, so this body A is moving faster as compared to body B. So just visualize here, because A is on top of B and it is moving faster. So there is relative motion between the two bodies. The bodies are rubbing against each other. So there is some relative motion. So this friction will be kinetic friction. And we have seen here that the work performed by kinetic friction is negative. So we conclude that the total work performed by kinetic friction is negative. And okay, we are making observations. Let us be clearer that we are making observations with respect to ground. So we are making observations with respect to ground, and we are saying that the work done by kinetic friction is negative. Okay, this is always correct, that the total work done by kinetic friction is negative. But what about the work done by this kinetic friction on one object? The work done by kinetic friction on body A is negative. So this means friction can kinetic friction can perform negative work on a body, but work done by kinetic friction on the other body is positive. So this means that the kinetic friction can also perform positive work on a body, but the total work performed by friction, kinetic friction, will be negative. Okay, I would like to emphasize one more thing, that it also work will depend upon the frame of reference. Because if we change our frame of reference and we make observation from, say, one of the bodies, say the observer is somewhere here, then to this observer, body A would appear to be stationary. So this observer will say that although a force is acting on my body, on this body, but the body is stationary. Although frictional force is acting and other forces may also be acting, but the body is stationary because he is making observations from here, from the frame of the body. So he will say that although friction is acting, but the point of application of the force is not moving, or the body is stationary, the point of application of the force is not moving. So the frictional force will not perform work. So this observer, who is right on top of block A, will conclude that frictional force is not performing any work. And if the observer is on the ground frame, then he will conclude that frictional force is performing negative work on the body. So this is another conclusion that we draw, that work is frame dependent. It depends upon the position of the observer. Okay. Now what happens if these two bodies have same velocity? So say V1 is equal to V2. So the bodies are moving as a single entity. There is no relative motion. So static friction will act between the bodies. But if V1 is equal to V2, then suppose V1 is equal to V2, it's a special case. V1 is equal to V2. So this will be 0. So we will conclude that the net work done by static friction, or the total work done by static friction, is 0. Because let us say that V1 equal to V2, since both are same, then there will be no relative motion. Hence, the work done by static friction is, from this relation, it is 0, because V1 is equal to V2. But what about static friction? Because there is no relative motion, so static friction must be acting at this interface or may not be acting, because this value of the static friction can be anything between 0 to mu s into n. So static friction may be 0, may not be 0 at this interface, but it will not perform work anyway. If we write this equation in vector form, and let us say that both the bodies are moving with different velocities, just take this general case and revert to this general case again, and then write the work in vector form. Work performed by this force on this body will be F into V1 dt vector F vector dot, and the work performed by friction on the other body will be, let us call it F1, and the work done by friction on the other body V2 dt. But because F1 and F2 will always act in action and reaction pair, so F2 vector will be equal to minus of F1 vector. So it boils down to, this boils down to minus of F1 vector into V2 dt. So now it becomes F1 dot V1 minus V2 dt. So it becomes F1 dot. Now V1 minus V2 is the relative velocity between the two bodies. So let us call it V relative. Now if you use the formula for dot product here, then you will get mod of F1, mod of this, into mod of this, mod of this, into cos theta into dt. So what is this? This is the speed of the body. It's relative speed between the two bodies. This is the relative speed. This V relative, mod of V relative is the relative speed between the two bodies. So this relative speed into the time dt, if you club these two terms, then this is relative speed into the time, into differential time, will be the relative distance, which will be equal to the distance between the two bodies. So, and the distance between 2 points, or distance between two bodies, as in our case, will be definitely independent of the choice of the frame of reference. So this is a very fascinating idea, because this vector, this is the speed, and if you club it with this dt, then speed into dt, this is the distance between, because this is the relative speed into dt will be the distance between 2 points, which is independent of the frame of reference. The distance between two particles, like the distance between your eyes, will not depend upon the frame of reference. It is an invariant. So this is a very fascinating idea, that the total work performed by friction doesn't depend upon the frame of reference. As in our case, you can see the total work. The work done on a body by friction may be positive or negative, but the total work done will not depend upon the frame of reference. So what are the ideas, or what is the conclusion of today's lecture? What is the synopsis? The conclusion is this, that the work done by kinetic friction on a body can be positive or negative, but the work done by kinetic friction on the entire system will always be negative. Work done by static friction may be positive on a body, and it may be negative on a body, but the total work done by static friction will always be zero. Fine. And total work done by friction is independent of the frame of reference. So these are the conclusions that we are drawing from today's lecture, and I think this work done by friction is clear to you, and the other concepts that we discussed is also clear to you. And thank you very much for today's lecture.